In this example, we'll use the average value of a function to find the average daylight for the days in January and February of 2012. The thing is, just what's illustrated here is the way we would go from actual data to a function, a mathematical model for the function, and then from the mathematical model we can use the ideas we developed in calculus to estimate this value. The data I've gotten is from this website here. It's a United States Navy website, and it basically, for this area, I believe this was for Palatine, it gives the hours of daylight. I'm sorry, it's storming out today while I'm recording this, but it gives the number of hours of daylight for each day. Let me show you the data. Here it is. So on January 1st of 2012, there were 9.2 hours of daylight. On the second day, January 2nd, there are 9.216 hours of daylight. Notice the days are getting longer as they do in January. The shortest day is about December 21st. And it keeps going like this. If we look at this, I've plotted all these days, and there's a little bit of code in there that I have. And when I plotted all these days, this red plot is the plot. I'll show you a little bit of where this function that I have listed up here comes from in just a few minutes. But let's start to take a look. Notice it looks like a sine function that's been shifted, or cosine function, but I'm using the sine. So let's take a look. If we look through those numbers, the data here, the longest day was 15.2167 hours of daylight, and the shortest day was 9.133 hours of daylight. To find the function, to find to come up with a model, we have to first of all find the baseline. Let me turn down, I'm using a different computer today, so let me turn down the baseline. And the baseline will be halfway between the smallest value and the largest value. So let's see, so to find the baseline, I'll average those. That will give me the number halfway between. And so I'll add them together. And divide by 2. Add these together. Let's see, what will I get? Well, I've rounded one to one place here. I have forgotten about this digit because basically so I'd have the same number of significant digits here. So what I'll have here is, well, 7 plus 3 is 10, and carry the 1, so the 1 and 3 is 4, and 6 is 10 again. Again, carry the 1 and 3. 1 and 3 is 4, and 1 is 5. Okay, and then I have a 1 and 2 is 3, and a 9 and 15 is 24. So I have 24.35 is the total, and I divide by 2. 2 goes into the 24 12 times, and 2 goes into 35 17 and a half times. So we have, this is our baseline, 12.175 hours is a baseline. So I'll have to add that to the sine function to translate it up to that level. The next thing we'll need is the amplitude. And the amplitude we would get would be the distance between the baseline and the top, the crest, or the distance between the baseline and the trough. Or we could take the distance between the trough and the baseline and divide it by 2, which is what I'm going to do. So our amplitude will be this 15.2167 minus 9.1333 divided by 2, and that's going to 7 minus 3 is 4, 6 minus 3 is 3, okay, 11 minus 3 is 8. I've borrowed the 1 from the 2, so I have 1 left. 1 minus 1 is 0. And then 15 minus 9 is 6. So I have 6.0834. And then dividing by 2, well, 2 goes into 6 3 times. And then I'll have 2 goes into 0.08, 0.04 times. And then the 34, 17 times. So the amplitude is going to be 3.0417, and these may be off a little bit from the values that I have here in this, and that's the reason for that is because of the rounding that we did on these numbers, and so notice that they're pretty close. This, if I rounded it to the next place, it would be a 7, and this one I think is exactly what we had in the other. All right. The next thing we have to do is we have to look at the phase length. For now, the actual period of the daylight hours is about 365.25 days. This 2012 was a leap year, so we have 366 days, 366 data points. So I'm going to consider it'll be close. It shouldn't be off too much. It'll only be about a 0.1% off. But I'm going to consider this going from 0 days to 366 days. And so we have to see if t is our variable here. T goes from 0 to 366. Now, by the way, if you've taken to statistics course, to go from discrete data, because we have a discrete number of days, we don't have, we have a first day and a second day and values, but we don't have a half day in there. All right, to a continuous number of days, there's usually a little bit of work we do, but I'm not going to bother with that. I want us to keep this basically as simple as we can. There's a fair number of details just to start with. So what I want to do is remember the angle for the phase for sine. A period is 2 pi. So what I need to do is I need to convert this from t that goes between 0 and 366 to some expression involving t that goes from 0 to 2 pi. And I can do that by, first of all, dividing through by 366. And I have 0 would be less than or equal to t over 366, be less than or equal to 1. And notice as t now goes from 0 to 1, all right, as t goes from 0 to 366, this expression goes from 0 to 1. We need it to go between 0 and 2 pi to complete one period of pi. So I'll multiply through by 2 pi. 0 times 2 pi is 0. All right, is less than or equal to 2 pi times t over 366 is less than or equal to 1 times 2 pi is 2 pi. So this expression 2 pi t over 366, as t goes between 0 and 366, this expression is going to go between 0 and 2 pi, and sine will complete one period as we wanted it to. Now there is something, 366 is an even number, so I think that I can cancel that off, and I believe that would leave, check me though, a 183. And so as t goes from 0 to 366, this expression pi t over 183 will go between 0 and 2 pi. And let's see, I believe that if we look at this, that's the expression that we have so far. Notice the amplitude, and then I have the change in period, and then the baseline change shifted up. And now the thing is, what I'd like to do is, let me look at this function. This function will be in blue, all right? And notice it's not in the right place. I need to shift it over to the right a little bit. So let's start to shift that over and see if we can see, all right, about where this would be. And I think that that's about as well as we'll be able to do. Notice they match up pretty well. We've shifted it over 81 days. Now let's think about that. Remember, it was at the baseline. Okay, it was at the center, all right? Okay, and the thing is, the place of equal daylight, equal darkness was about 12, was at the center here, and we shifted it over. All right, 81 days. And if you think about that, that's how far we would have had to shift January 1st, all right, to get it to the equinox. I mean, so if you shifted through January, that would be 31 days. We shifted 31. Then February, because we were in the leap year, was 29 days. 31 and 29 is 60. But then we have to shift it all the way to March 21st. So 60 and 21 is 81. So notice the shift would be over 81 days. And so here is the function, all right, that we can use, all right, then to calculate the average value. So this is, I've already accomplished the phase shift. And here's that function that we can use. Now let's calculate the average value. And I have done all the work here, so it'll be there for you. All right, so our function is, well, we've developed it here. You saw how we did it. We calculated the average of the max and min to get the baseline. We took the max minus the min and divide by 2 to get the amplitude. We made the period correctly by dividing by this, or time multiplying by pi and dividing by 183. And then we shifted it 81 days to the right, okay, so that we'd be in the right place. And now, here's the thing. If we look at this, if we want to calculate the average daylight that we have in January and February, well, January is 31 days and February is 29 days. So we're the 60 days altogether. So we're on the interval from 0 to 60 days. So I would integrate this and then divide by the interval length, 60 minus 0. And if we do that, and you can perform this integration on your own and come up with this, we'd have about 9.94125 hours of daylight. And this is how people go about things. You know, they lots of times, what we did, we came up with a mathematical model from data, and then applied our mathematical ideas, in this case the idea of calculating the average value of a function, to that model. And of course this won't be completely accurate, but it will be close. It will be very, very close. And usually that's what we're trying to do, is get an estimate. Okay, we'll do another example in the next video that will involve household electrical current.